Hey guys, it's Mr. Sheeline here. This is going to be a video for anybody who wasn't in class or um, possibly just forgot what I talked about in class when it comes to some derivations to some equations that we're going to be going over in class. I guess it'll be on a Monday, March 22nd of 2021. So let's just get to it. So this is a slide presentation that I found. Oops, here, let me change that. Um, that I found from a Better Lesson or a teacher from Better Lesson. It's a really good kind of summary as to how it is that we can find out what we're going to calculate, which is specifically going to be the orbital velocity and also the period, the orbital period of an orbiting body. So let's see here. I'll go back a little bit. So this is what it is. We're going to try to derive the velocity and period of a satellite in circular orbit. Now we're going to work on a very specific worksheet in class so we can kind of get an idea of what we're doing. But this is going to be a video that pretty much just covers how we derive the two equations we'll need, specifically the orbiting velocity equation and then the orbiting period equation. So, and as we already know, we remember Newton's law of universal gravitation is this right here. It's F is equal to big G, our universal constant, times m1 times m2 divided by the, here he has d, it's just for d for distance, when that's supposed to be radius, the distance between the center of mass of one object and the center of mass of the other object. Okay, I'm sorry about that. Okay. And he does have to say it right here, the distance from the center of mass from both masses. And just a visual that he puts in here. Just always remembering all of this. Okay. And we don't need to do this. But if you were to wonder what that is, roughly speaking, the force of gravity between you and the Earth is roughly about 600 newtons. Versus, say, you and a friend that are 1 meter apart, roughly speaking, would be, here's the difference between it. And all it is, so all this is setting you up to understand the difference between two differing objects and seeing that there's a discrepancy in the amount of force based upon not only the distance, but also distance from center mass, but also the relative masses of both objects. Okay. Now, when we are talking about orbital velocity and period of say satellites, or and satellites in the technical term, satellites as in the orbiting the orbiting body that is being influenced by a very and is being held within a particular track, like a particular path that is shaped by a larger mass. So this will be talked about both in relationship to satellites that do go around the Earth, such as like actual technology like satellites for imaging, for TV, for communication, but also for satellites such as the moon, orbiting bodies such as that. And also it will be seeing the orbiting bodies such as like the Earth, Jupiter, Saturn, Neptune, Uranus around the sun. Okay, now it does rely on these two things though. These derivations require that A, number one, the satellite has to have much less mass than the body. So that means that M1 here has to be significantly smaller than M2. Okay. Number two, the orbit has to be circular, relatively speaking. Now we know that for the most part, the moon does not travel around the Earth perfectly in a circular path. The Earth does not travel around the sun in a completely perfectly circular path. But roughly speaking, it needs to be decently circular. Okay. It can't look like this. You couldn't, here's what it couldn't be. Just so we're clear, it couldn't be this. It couldn't be that you have, and it comes like where you have a massive difference in these bodies trying to find equilibrium. It's really to say this. It's to say that you need to have you have to have this object in a roughly equilibrious path. around another body. That's really what we're saying here. Okay. So it has to kind of travel as such. Okay. So average orbital velocity. So remember here, we could derive the force of gravity, the attractive force between this object and this object. And that should be, these are roughly the same size, using this equation. But we're going to add in a second equation, and that is specifically going to be the centripetal force equation. Now, we saw before in a worksheet that we noticed that the centripetal acceleration when we're standing on the surface of the Earth is very different from the gravitational force, or I should say the gravitational acceleration. The acceleration due to gravity are two very, very different things. And here, then we're going to say, okay, well, if that's true, if centripetal acceleration on the surface of the Earth is super duper different than the acceleration due to gravity, how is it then that we could somewhat compare these two things right here? Because that's what we're ultimately going to do, and this is why. Because one of the conditions is that the objects that we are looking at, are one of the satellite is in a circular path that it's significantly smaller. Not only that, it's the key that it's on a circular path around the object. Before, we were working with something that was like, say, right here, right? It was on the surface of the object, and it was relative to, the center of the object. Finding this tangential velocity, finding this centripetal acceleration is very, very different. If I can get this guy to stop, I don't think I can. There we go. Is very, very different between the centripetal acceleration of a separate entity traveling independently, or at least separately, physically separately from another one that has this force. So it's two different forces. It's two descriptions of two different kinds of inertial states is really what it is. So in this case, because we're going to have two objects traveling in different ways between one another. We'll have one that's relatively just kind of staying put, relatively speaking, one that is traveling around the larger object due to its larger mass. We're able to make a bit stronger comparison between this equation right here and this equation right here, which is specifically going to look like this. The centripetal force, as we should know, is going to be reliant upon, and specifically of this body, okay, like our rubber stopper that we've been playing with, will be the mass of this object times its tangential velocity divided by the distance between here, the center of this object, to the center of whatever the body is that's holding it within this circular path. And so what we'll be able to do is this. We're going to be able to say that, well, the centripetal force of this orbiting body is going to be equal to that gravitational force. And we can then derive some equations from that. So we'll set it up where we'll say that the centripetal force is equal to m1 times v2 squared over r. The gravitational force is equal to what we've been working with, g m1 m2 over r squared. And we'll more or less then just break it down to where we then solve for v. We solve for the velocity of our object. And what it ends up being is that we're going to say that the velocity of our orbiting object is going to be contingent upon the square root of big G, our universal constant, times the mass of our second object. Okay, the second object, the one that relatively speaking doesn't move. Okay, divided by the distance between them, okay? And using this, we'll be able to figure out just how fast something is moving around another body. So again, we can then determine how quickly imaging satellites are traveling around the Earth. We can determine how quickly it is that the moon is traveling around the Earth. We can figure out how quickly the Earth is traveling around the sun. We can use this equation here to figure that out. Okay. Now, then we can take this, and then, so that's finding velocity, the orbiting velocity. We can then just determine, well, really this equation here is just distance over time, is really what it is. We're saying this is how quickly this object is going to move at this kind of, in the circular path. This is how quickly it's going to move over that period, or the amount of distance will go over time. So we could then say and derive this is to say, well, that would just be, the velocity is equal to 2 pi r over t. So this is to say, here is the distance of a full circle, and then here is how long it takes. How long does it take for us to go into rotate perfectly around that one circle, or not perfectly, but how long does it take for us to go around the distance of the circle? And so we'll set those equal to one another, okay, in order to find our period, because we want to know what our period is going to be, okay. And the way that we would do this is to say, well, if we're looking for t, we're just going to make the inverse of both sides here, just so it's a little easier. And then we just pretty much slap this guy over here, but we're not done yet, because then we can see, oh, well, r is in a couple of places, okay. So r is in a couple of places here. Let's see what something's missing. What's missing? I'm just looking at something real quick. Just trying off the top of my head, remembering how it is that we get the r squared. Oh, we just get the r squared. We just get the r squared in here because we're trying to factor in. You just don't, when you have all this whole dude being square rooted, you just can't toss this in willy nilly. In order to account for the square root, in order to kind of counterbalance it so it remains as r, you have to slap it in as r squared. Which then, once you slap it in as r squared, then it becomes r3. But honestly, it's don't worry. All I'm saying is don't worry. It works out. Algebraically, it works out. I'm just trying to remember how to explain it. But anyway, slap it in. Doesn't matter, because honestly, how we get there, as long as we know that this is where we get to and what we're going to be using. Okay. And this is it. It's going to be the period of the orbiting object, the time it takes in order for it to move around a body. This is what we would use. We're going to use 2 times pi times the square root of the distance between the two objects cubed divided by big G, universal constant, times the mass. Now, remember, here we've lost the little number, but don't forget, it's specifically going to be the mass of our second object. I don't know why he takes it out, but it's the mass of our bigger object here. So always remember that. That is m as in bigger object. So if we're trying to find the period of a satellite, this is m2. This is m of we'll say the Earth. Okay. So don't forget about that. This is the mass of the Earth, not just mass of our object anymore. Okay. And so then here we have it. We have the two equations we'll need, the orbiting velocity, and this is how we would find the orbiting velocity versus the period equation, where we will find how long it takes for this object to move around the larger object. Okay. And remember, it relies on these two things. It relies upon the satellite having much less mass of the body. And then it also requires that the orbit is circular. Okay. Relatively speaking. And that's pretty much it. Those are the two equations that we're going to take a whack at. And we're going to work on one of those. We're going to work on a problem to get more or less together in class. If you're at home, try your best. Hopefully it isn't too difficult. Check out the directions on the assignment that's being posted on, or that was posted on Google Classroom, so you can just give it a try on your own. If you do have any questions for me, make sure you ask me anything that you may have. Other than that, that's pretty much that is pretty much the end of the video here, guys. So if you still have any questions for me, make sure you get a hold of me. If not, I'll see you in the next one.